I was asked to do a presentation on the battery presentation. I originally did this presentation for Aries many years ago, and then I was asked to present at Rocky Mountain Ham Radio at their university class. So I redid the presentation entirely and updated it for lithium battery chemistries and updated a bunch of stuff. It became almost 3 hours long at that point, so it's been cut back down to fit in the time frame that we have today. But if you're interested in the deeper program that has more details, it is available on the rmham.org website under the, I think it's archives section. But in the meantime, let me get this thing shared and we'll start.
Darren, when he gets done, I have something of importance I need to pass out.
All right.
All right. Everybody see the presentation now? Thanks, Darren. Let me shrink this up just a little bit. Okay. So we're going to talk about batteries that we typically use in our amateur radio hobby. We're going to focus on two main chemistries today, lead acid and the various types, and some lithium chemistries. We'll start with lead acid and then we'll move into the lithium side. But, you know, in the lead acid side of things, there's basically three main types of batteries. We have the flooded batteries, meaning that it's full, you know, it actually has an acid water liquid in the battery, like your typical car battery. And then of course there's subtypes of those, a starting battery and a deep cycle battery. The Agm battery is an absorbed glass mat. Same exact concept as flooded, except instead of a liquid floating around loose, it is absorbed into typically a fiberglass mat that's tucked into the battery between the plates, and then a gel cell. So typical battery is made up of 6 cells inside of that big plastic case that are approximately 2 volts each, making it a 12-volt battery in series. The positive terminal is lead dioxide, and the negative terminal is porous lead. The electrolyte is about 6 molar sulfuric acid and water. So, you know, here's a very simple drawing of what this looks like. This would be a single cell in a whole battery. We'd have 6 of these together with the internal connections between the plates. And as you notice, the anode and cathode here, the positive and negative electrodes are made out of slightly different material. That becomes important here. So let's talk about the difference between the two types of batteries. Of the flooded, the starting battery has many more plates, and they are much thinner. The reason? They provide much more surface area, which will deliver much more current. However, they're easily damaged by a heavy discharge. The plates will warp. And they can warp enough to touch each other, in which case the cell becomes shorted and the entire battery drops by, you know, approximately 2 volts. And then it becomes a giant resistor where the rest of the battery is heating that cell. It's designed to deliver a very high current for a very short period and then be replenished immediately. Now, a deep cycle battery has fewer plates and they're much thicker. It does mean that they're usually not able to deliver as much of the heavy current, but the plates are thicker, so they resist warping and they can be discharged further than a starting battery. They deliver lower current for a longer period of time. And just for rough numbers, a deep cycle battery, to keep it healthy, you should never discharge it more than 50%, and a starting battery should never be discharged more than 20%. So let's look inside the battery a little bit. We won't get into the deep chemistry here, but there's some important things that happen in here, and it explains why these depth of discharge is so important. Connection of an electrical load allows the electrons to flow from the negative to the positive terminal of the battery. This reduces the charge and the voltage at the electrode. The chemical reactions are able to proceed, generating new electrons and generating the power that is converted to electrical form to drive the external load. Now, this is the key piece here. As the battery is discharged, the electrodes become coated with lead sulfate, and the acid becomes weaker. It is converting the acid into lead sulfate, which is coated on the plates. Now in charge, imagine that, exactly the opposite happens. So we connect a battery charger to this. The whole chemical reaction takes place in opposite direction. And again, as the battery is charged, the lead sulfate coating on the electrolytes is removed and the acid electrolyte becomes stronger. We're going to get to why that's really critical here shortly. The state of charge. State of charge can be determined by terminal voltage. Now, of course, there's always caveats because nothing is ever textbook in our world. But terminal voltage of a lead acid battery is the de facto standard for determining the state of charge, how much energy is in the battery. Terminal voltage should be measured 1 hour after removal from the charger with no load connected. That would give you the most accurate measurement. And the term, that should be measured with no load, nothing attached. Now, this chart shows something kind of interesting. These numbers can be argued a little bit, but they're not off by much if depending on all the experts. The important thing here to look at the voltage of a fully charged battery to a completely discharged battery. 1 volt is all the difference in that. So if you have a car battery and it's reading 9 volts or something like that, it has been reduced way beyond what we would consider dead in the battery, and damage can happen. So that 12.7 to 11.7 is 10 volts is considered basically completely dead. So that 11.7 would be about the mid charge or a safe completely discharged battery. And you can see the specific gravity of the electrolyte changes as well. So what are the best ways we can damage our lead acid batteries? Number one, beyond all others, is over discharging it. Take your starting battery below 20%, take more out than 20% or a 50% for a D cycle. And leaving the battery discharged is absolutely the worst thing you can do. If you accidentally have a battery go much lower, as long as you get it charged back up, if you haven't warped the plates, you're probably going to be fine. But the key here is that the longer that the battery sits in a discharged state, that lead sulfate that's been coated on those plates gets harder and harder and harder, and it becomes insulative. So freezing is another one. If the battery is low, it's more water than it is acid, and it can freeze easier. So keep it charged up. And then, of course, overcharging, you can boil the battery and it will boil the water out, leaving nothing but acid, and that's pretty bad for your battery. Something to be aware of is the self-discharge rate. So typical lead acid batteries lose about 5% of charge per month at rest. The self-discharge rate increases with temperature. So for about every 18 degrees F, the self-discharge rate, that means that the battery will just become depleted, sitting there on the ground with nothing connected to it. The replacement cycle, if 30% of the charge is lost in the first 24 hours at rest, that's considered a battery that probably will not, cannot be relied on, and it should be replaced. Let's talk about capacity for a minute. Capacity is probably one of the least understood items and the most confusing items in batteries, because every battery, every manufacturer, and every type managed to somehow do it and give you different data on it, which does not help us a lot. But one thing that is known is the C rating. This is a constant current draw. So 1C would be a constant current draw level that will discharge the battery from full to empty in 1 hour. You will find almost all lithium batteries have a C rating printed on them. Almost no lead acid batteries have them, although you can figure it out. C is the capacity of the battery, but it's often used to describe the safe charge or discharge rate for the battery as well. Now, if we go to automotive batteries, which we use, right, sealed lead acid batteries or AGM batteries are something that we often use in our ham hobby, especially if we're operating field day or out in the, out remote, something like that. Those batteries usually are listed in RC or reserve capacity. And what reserve capacity is the time in minutes the battery can run at delivering 25 amps without dropping below 10.5 volts. That's an industry standard capacity, and it's used. Honest to God, I don't know why they use that capacity, in a starting battery. It's certainly more understandable in a deep cycle battery. But good news, if we want to use amp hours, which is the most friendly unit of capacity for ham use, we can roughly get there by that formula there. We take the reserve capacity times 60, which converts it to seconds. We multiply the length of time in the reserve charge, which is 25, and that gives you the number of coulombs of charge. And then you divide this by 3,600. That's the number of coulombs in an amp hour. So, little example here. Here's a pretty typical battery. And you'll see in the corner, it's got a 160 reserve capacity rating. So we take that times 60, that times 25, divide that by 3,600. We come up with 66.6 amp hours in that battery. I believe that this particular manufacturer does actually stamp the amp hour rating of their battery on it, and it will be slightly different than this. The trick to this is that capacity changes with temperature and load. We're going to talk about that next. 1C is a 1 hour discharge, so 2C would be the current required to discharge the battery in half an hour, or a half C would be a 2 hour discharge rate, et cetera, et cetera. Now there's this thing called Pukert's law that removes some capacity of the battery. This is where the real life aspect of this makes the real life connection to the textbook example. Pukert's law removes some capacity. There is this giant formula, and you can go through and figure out, because of the discharge rates and the temperatures and all these other things, why the discharge rate is not linear. The capacity of a battery will not be the same at a low current draw as it will at a high current draw. Pukert's law explains why this is and gives you a formula to calculate the approximate capacity at your current draw. There's a lot easier way to just make a quick guess. Use 80% of whatever the rated amp hour is, and that's a pretty safe capacity that you can expect to get out of your battery under almost all circumstances, as long as you're not using it for welding. So batteries will not, and this chart goes into explaining exactly that. This shows Pukert's law in action. Batteries will not deliver as much energy at the higher C rates. So lead acid batteries are often rated at C divided by 10. As you can see there, the 1 hour rate is 36 amp hours. But the 8 hour rate 49, 24 hour 56. It's not a linear across there. We're drawing less and less current as we move across the chart. Okay, so let's talk about the important parts of taking care of our batteries. That's one of the main goals here. Besides figuring out how big of a battery we might need for a job, we need to take care of it. Charging, there are basically three kind of main category chargers out there for lead acid. The bulk charger, these are often the ones you see that look like about a lunchbox size. They got a handle and they usually have a single ammeter on them, and they might have 1 or 2 switches that say 6 volt, 12 volt, or they might say automatic or starting. You know, they're very simple. They're cheap chargers. But used to buy these at the, you know, Sears type stores and things like that. Now you move on to a 3-state charger. There are chargers out there that will claim to be 4-state, 5-state, you know, things like that. But honestly, the 3-state chargers, there are 3 states that are the most important. We'll go through explaining what that is here momentarily. And the last one, which is not technically just a charger, is desulfator. All right, so in a 3-state charge, this is, by the way, what we want. These chargers here that I've listed as bulk charger, if you need to just get some juice in a battery to get it going and move on, those are fine to do. But do not leave a charger on. Do not use those types of chargers as a long-term maintenance for your battery. You will eventually ruin your battery doing so. Buy a good 3-state charger. 3-state charging, here's the 3 states. The first thing it does is we put a bulk charge on, and that charges the battery to about 80% of capacity. That is as high as those other chargers I just mentioned will ever get the battery. They'll never get it above that. This 3-state will then switch to absorption charge, and that will take care of that last 20%. And it will get the battery to an absolute 100% charge rate. And then the 3rd state is the float or maintain, where it provides just enough to keep it right at that 100% because of self-discharge, temperature swings, etc. In the bulk charge, we're going to put a constant current across the battery and measure the voltage of the terminals. Smart chargers, there are a lot of smart chargers out that have computerized this process to the nth degree now. But they'll start at a low fixed current and then step to a larger current so they don't damage the battery if it's heavily discharged. Again, that plate warping thing, that can happen when it's charging too. So we bring the battery up very slow. And then once the battery's at the point where it can be healthily charged at a decent current, the charger will do that. Once the terminal voltage is at a determined level, and it's determined that it's about 80% full, it will switch to absorption charge. This is where we go from 80 to 100. It is often the slower part of the charge. It is a constant voltage, and it is typically very high, sometimes 15 or more than 15 volts. Now, one thing to be aware of here is if you're putting this charger on a battery and that battery is currently powering your ham electronics and things, be a little cautious of this, because 15 volts, 16 volts, some of that is too high for a lot of our ham gear and it will damage it. So be a little cautious about your charger. And over 15 volts, if you have a gel battery, it will destroy it. And so at this level, since we have a constant voltage, now we just measure the battery's ingest of current to determine where it's at in that 80 to 100% level. Finally, we switch to the float or maintenance. And this is current limited and usually no more than 10% of the bulk charge rate. If it needs more than that, the cycle will drop back and start bulk absorption and float again. The charger only delivers as much charge as the battery requires, which means that as temperature swings change during the day, it will maybe deliver a little bit of current to the battery. However, when the temperature swings back the other way and now there's excess energy, the charger has to be capable of delivering 0 amps to allow the battery to naturally migrate back down to essentially 100% charge. Battery charge rate and the capacity will change on temperature. High quality chargers will temperature compensate. Really high quality chargers have a temperature probe that you can stick on the battery and it will read the actual battery's temperature itself. Although, to be honest with you, for the batteries that we use, the internally compensated ones are plenty good enough. Now, we mentioned at the beginning of this about desulfation and the lead sulfate that built up on those plates. And if it stays there too long, it becomes hard and insulates the plate. So some chargers can desulfate. There are also dedicated desulfators. And what they do is they will either pulse DC or they'll actually pass a low current AC for small time periods. And the idea is, and we know about this from RF, from sine waves, anything, right? When we pass a sine wave through a material, that material actually vibrates at that frequency. So if we pass a small AC current through the plates will micro vibrate to that, in sync with that AC current that's thing. The idea there is to just provide just a tiny little bit of movement to help knock some of that hardened lead sulfate off the plate. And if it's not too thick, it will fall to the bottom of the battery and it will eventually recombine with the electrolyte. Some smart chargers will do this anyway, even if the battery's never been discharged heavily, or is not recovery. It'll do that just as a health check to make sure that there isn't any sulfate that builds up. It's much easier to remove if there's a tiny bit of soft than a hard coating of thick there. Again, it is not an end-all solution. It works for light sulfation. I have seen people actually take these batteries and either shake them or drop them from like an inch or two onto some 2x4s, just some physical thing. Again, not the safest thing in the world, but it can help knock the sulfate off a little bit. And of course, the bottom bullet, typical PSA here, right? Don't let your batteries get that way is the best way to keep them healthy for the long run. Here is a very popular charger manufacturer. Deltran makes all kinds of these. They've been around forever. Super simple. They're fairly inexpensive. This is a 3-state charger. If you go read the instructions about this, you'll see that when it's charging, the light will turn red. That's the absorption. The bulk. When it goes to absorption, that green storage light will blink green as it's charging from 80 to 100%. And then once it reaches the 100%, it goes solid green. So super simple, no meters, no switches, no anything. You just plug this thing in and leave it on your battery all winter long, whatever you're doing. When you're not using it, it's safe to leave these on. They make them in bigger banks. There's a 4-bank battery tender. It's got 4 of the same little ones in there. You can build your own. I have built many of these, and there is, believe it or not, an IC chip that's its only purpose in life is lead acid battery charging, 3-state with temperature compensation. Now, if you want to spend some money, there are certainly chargers out there that will allow you to do it, but they add all kinds of really neat computerized analysis of the battery. Some of these chargers measure internal impedance, and they will determine how much and if desulfation is needed, and they'll adjust the voltages and currents dynamically with the state of the battery, the temperature, you can see this charger's got cold or AGM settings. This one's actually got lithium settings. It's got jump charge. This is a pretty neat charger, but the price goes up pretty fast. All right, so let's just summarize where we're at with lead acid here. Keeping your batteries on a smart 3-stage charger at all times that they're not being used is the #1 way to keep them healthy. #2, use them once in a while. That is actually healthy for the battery to use it once in a while. And if possible, load test it once a year. Does it still deliver the amount of capacity that you think it will? Be kind of bad to find out when you take it out to field day or out to a Aries event or a bike race that you're supporting and it's got 1/10 of the capacity left. There's a couple ways of lead test capacity testing them. The West Mountain CBA, and by the way, folks, all the brands and things that I use in here this is not an advertisement for them. I've picked them because I have experience with them and have had good luck with them. So, I'm just passing along information about that. The West Mountain computer battery analyzer is a really neat little way to do it. If you don't want to spend that money, you can use a car headlight as a discharge device. Just watch your voltage real close so you don't discharge or too far. That's what the little CBA4 looks like. You plug a battery in and it hooks to the USB of your computer and it plots a real chart of the whole discharge for you. All right, let's move on. Lithium, a whole new world and a whole new set of pros and cons. Now, in this section, you're going to notice a lot of emphasis on safety. If you think a big heavy battery full of liquid acid is dangerous, it's probably significantly safer than most of the lithium chemistries if they're not treated right. All right, I'm not going to read all of this to you. The slides will get posted on the website so that you can follow up on them. But essentially, we have the same type of reaction happening in a lithium battery as we do a lead acid. All the materials are different. So we're moving ions back and forth between the terminals, and the terminals are typically graphite. And then there's a lithium-based paste in the middle. Intercalation is what it's called when the ions are charged. The interesting thing here is that the ions actually will be held inside of a sort of crystalline-like structure in the host material without significantly disturbing it. That actually plays a lot into why lithium batteries have such a higher density, power density. So we move back and forth just as we did in charge and discharge. It's an oxidation reaction that occurs in the battery. Again, I won't read this to you with all the boring chemistry stuff here. During the charge and discharge process, we're still moving the electrons back and forth, and because of basic chemistry here, we have to, for each, every molecule that has that is disturbed, we have to move. I'm sorry, I just derailed in the brain there. Electrons are free to travel, so the positively charged ions that will balance the movement of the negative charge. That's where I was trying to go there. So as we move the pieces across the molecules across the medium, we're knocking electrons off and regaining them so that everything stays stable in the battery. One of the things here, the transfer of lithium ions between the electrodes occurs at a much higher voltage than in other battery types. So a single lithium ion cell can produce a voltage of 3.6 volts or higher, depending on the cathode materials. Think about an alkaline battery. Our old true trusty alkaline non-rechargeables are about 1.5 volts. Lead acids 2, and these can be 3.6, 3.7. I mentioned the anode is usually graphite. Now, this is the one thing about lithium ions. The repeated insertion of lithium ions into the standard graphite structure, it eventually breaks apart the graphite. So, one of the terminals inside the battery eventually breaks down, and that's ultimately one of the typical failures for a lithium battery. Now, there are so many different types of lithium, and this is not even touching the surface, but these are the 4 probably most common types that you'll find. Lipo, or lithium polymer, huge in the RC, radio controlled car, plane, and drone industry. Solid electrolyte makes the battery safer than liquid, but it's often contained in a soft flexible pocket. So it's a little bit more prone to puncture, which is super dangerous with these. The lithium iron phosphate has a higher discharge rate because it's capable of a higher temperature coefficient. It's stable. It remains stable over a wider range of temperatures. So it has a longer life cycle, but it does self-discharge a little faster than lipos. As we move up the chain here, we've got lithium manganese oxide. And this is, again, a safer cell, but it has a lower capacity and usually an overall shorter lifetime. And then we get into lithium nickel manganese cobalt oxide. There is a whole string of letters that don't belong together, all jammed into one there. Nickel is a real big game changer in the lithium scene. You've got much higher current flows, longer life. The overall capacity of the battery is typically increased. A lot of electric vehicle batteries are typically this chemistry. They're the most expensive to manufacture, but you know, they're better in almost every way. So let's talk about this. We know that lithium energy densities are significantly higher than other chemistries, right? We have more amp hours in a smaller and lighter battery compared to lead acid to any other battery. We can discharge huge discharge rates out of these things, sometimes 25, 30, maybe 50 C of the battery. We don't have memory problems in lithium at all. NiCads, you may have remembered the old NiCad days. If you discharged it 20% over and over and over again, that became the entire life of the battery. So you had to do a deep discharge on those every once in a while. So it seems like these batteries are better in every way. So what's the catch? They're dangerous. They are very, very dangerous. This is a Colorado ham that had a battery spontaneously melt down just sitting on his ham desk overnight in the middle of the night. We'll get back to that in a minute. Probably seen YouTube videos of people that have either cut or punctured batteries to their lithiums with nails, or I've seen people saw through them with skill saws. Well, this is a pretty typical reaction for a battery that has a thermal runaway because it was punctured or damaged in some way. Remember, we talked about that high rate of transfer of energy within the electrolyte between there. Well, the reason the battery stays safe is that those cells are very small and contained. When you puncture the cell and you produce a large amount of electrolyte, you know, in its area, we really increase the energy transfer rate so high that it can spontaneously explode. What are some of the other cons? Now, there's some caveats and some updates here, even though this is an updated presentation. You have the safe containment for charge, discharge, and storage, absolutely necessary. The shorter life is becoming almost becoming almost untrue anymore, and there are a lot of lithium chemistries now that will outlive, and it will have many more cycle capabilities than lead acid. Not all of them, but certainly the technology is skyrocketing right now. This one is key though. You have to store the batteries at a reduced charge or they will eat themselves. Remember we talked about the graphite falling apart as the ions were intercalated in there. If we have too many of them at one pole of the battery, the battery self-destructs faster. So we have to store them at a reduced rate of charge or reduced level of charge, state of charge. Charging is absolutely critical that you use the right charger. If you charge a lithium battery that doesn't have self-protection devices built into the cells with a NIM or a lead acid charger, you can easily cause a huge explosion in the battery. And really, you have to balance your packs to maintain safety and longevity of the pack. What that means is make sure that each cell in your battery that's connected remains at extremely close to the same voltage level as all the other cells in the pack. So they're constructed with the same type of, the same idea. We have plates with an electrolyte and terminals at each end. But on the left, we have a typical lead acid battery. On the right, it's a polymer, a lithium-based one that's stacked inside of the, with film inside of a little package. Big chart of pros and, pluses and minuses here, right? Lithium's got a higher power density, higher discharge rate. Typically, they are a slower recharge rate. That's one thing where lithium differs. You it's almost kind of hard to hurt a lead acid by putting too many amps into it to recharge it. It's possible, but it's far less. Lithium can be damaged if you it can explode if you put too high a charge rate into them. It can discharge very fast, but they don't like to be charged very fast. You need a special charger. Storage at less than 100% is needed. Balancing. The shorter lifetime, again, is kind of not really, it's becoming not true anymore. And much higher safety considerations. Again, you've got a battery full of liquid acid. If you drop it, you're going to have some liquid acid on the floor to clean up. If you puncture a lithium, you may have an explosion on your hands. So significantly different there. Let's talk about why lithium batteries are, and what's some differences in purpose as far as they fit into our hobby, which, as we know, is a 13.8 volt hobby, a 12 volt hobby. So lead acid nominal terminal voltage is 2 volts per cell. Lead acid batteries do not typically advertise the number of cells, right? We don't see a 2 volt times 6 car battery. It's a 12 volt battery. Nickel-based batteries are about 1.25 volts per cell. So when we put these together, if in a car battery we put 6 cells together at 2 volts, we get 12 volts in series. The nickel-based batteries, we put 4 cells in series at a 1.25, we have a 5 volt battery. Let's move into why lithium changes the game here a little, and some cautions. Lithium chemistries usually list the S count instead of the voltage. That's the cell count. Each S is a single cell. Lipos have a nominal voltage of 3.7 volts per cell. So 4 cells in series at 3.7 volts is 14.8 volts. Now you see LiFePos, the lithium ferro, LiFePo 4 batteries have a 3.3 volt per cell. So when 4 of those in series, we get 13.2 volts. Now, I said the S was for cell. You may see P too, right? So S is series, P is parallel. And this is how they would be wired. You'll see the heavy leads are connecting the batteries in series together, each of the tabs of the battery together, with the power connector being the orange one in this case. And the little gray one at the bottom is the balance connector. A 4S2P means there are 4 cells in series with 2 parallel sets of cells. So a 4S1P is 4 cells, 1 parallel. It's 1 set. Nothing's really parallel there. But a 4S2P would be 2 cells. So each pair of cells are tied together, doubling our current capabilities of the battery. So you have a 10 amp battery on the left, a 20 amp battery on the right, at the same voltage. Now, don't fall for the nominal trap. This is where we have to be a little careful with lithium in our hobby. Nominal simply translates to named and is used in place of the voltage to place the battery in a voltage class. Let's take the Lipo. Lipo nominal voltage we just talked about was 3.7 volts per cell. So 4 volts in series at 3.7 is a 14.8. But in real life, a fully charged Lipo is 4.3 volts. If you put 4 cells in series, we're at 17.2 volts for a 4S battery. That is way too high for most of our ham gear. 15 volts is usually pushing it for things like mobile transceivers and things like that. Now you say, all right, well, we take 3 cells and are now fully charged is 12.9. Problem with that is that now when it's as it falls and it becomes low, it's going to be under 10 volts. It's too low when the battery, we won't get the same range out of it. So those are not very friendly numbers for our 12 volt devices. So let's take a look at LiFePo batteries, which have a 3.6 volt nominal. 4 cells in series, 3.6 is 14.4 volts. So that is much more friendly to our 12 volt devices. We start at 14.4, we end at maybe 11.9. very friendly range, Lipo batteries. On top of that, they're safer. So good choice for amateur radio activities. Now we'll move into charging considerations here. You have to use a special charger for lithium chemistries, unless the battery has its own battery management system. We'll talk about that in a moment. Typical charging of lithium chemistries, there are typically 3 types of charge. A fast charge charges at very high C rate, although still a safe C rate for the battery. This is very similar to that bulk type charger we talked about for lead acid. It gets the pack up to 80% as quickly as it can, and then we just skip the 80 to 100% charge. Lithiums typically are more of a 2-state charge than a 3-state charge, but it still applies that 80 and 20% mark there. A normal charge takes the battery usually at 1 C. So if you have a 5 amp hour battery, you would charge that at 1 C, 5 amps. And that will take the cells through the 3 or 4 states of charge all the way up, gets to 100% and maintains it. It does take longer than a fast charge. Then the balanced charge, which is the slowest and healthiest charge of all, it has all of the same types of charge, but at certain areas of the charge, it will actually either place a small raise the voltage or place a load across each of the cells through that balance connector, and it will level off the voltage on every single cell until they're exactly the same. This makes sure that every cell gets the same voltage and charge level, and that will significantly increase the life of your battery. It is also safe, a much safer battery if all the cells are the same voltage. Why is it important to balance charge? Well, if you think about it, if you've got 4 cells in series and no load connected, if one of those cells, for whatever reason, becomes heavily discharged or much more discharged than the other cells, when you plug a load into that, the remaining cells are going to dump energy into that dead cell very, very fast. Remember, lithiums are capable of very heavy discharge, but they're not good at heavy charge. So if we have one cell that for some reason, whether it's partially failed or something caused it to go down, we can simply plug our load in and that battery pack can catch on fire as the 3 remaining cells dump energy at a much higher C rate than the battery can handle into that 1 remaining cell. If we're lucky, it'll just fail or cause a faster self-discharge. If we're not so lucky, it could certainly cause a fire. So that little white connector is the balance charge, and so you see there's a schematic diagram on the left that shows how that's put together. That is how the charger can actually look into a built pack and determine what the voltage of each one of the cells is independently. Now I talked about protection of cells. This is a little protection module for the battery. This is, as you notice, it's mostly round. This would typically sit on the top of a lithium cell, and each cell in the pack would have one of these. This device limits the amount of current coming into the cell itself to a safe limit. It limits the current exiting the cell to a safe limit. And some of these are actually capable of talking to each other and balancing the cell as well. So this battery pack made with cells with these little balance boards on them, it would be safe to just hook it up to say a 14-volt DC power supply and just let it go. And what you'll see there is the current will taper off and eventually it'll go to absolute 0 when each one of these little modules cuts the current off to the cells inside. Something like this, again, a Deltran thing, but this is basically a little motorcycle battery that's been put in the form factor that motorcycles or garden tractors would use. This is the type of battery that's got lithium cells in it in each one of the cells, or it's got a battery management system that's making sure that, because we know that you're going to hook any kind of charger up to this and it's safe. It will charge it up, and the battery management system inside will cut it off when it's done charging. and it will limit the discharge to a safe rate also. Okay, have we mentioned safety lately? They have to be charged, stored, and discharged safely and carefully. Batteries can fail at any time. Complacency in this area could result in loss of life or property. Remember this picture? This battery was literally sitting, it was a drone battery. It was sitting there unconnected on his desk at 4 a.m. and it decided to catch on fire and melt down. He was it set off the smoke detectors, which woke them up. And he reminds us that one of these saved his home and possibly his life. They were able to run downstairs and extinguish the fire. It certainly did a lot of damage, but no one got hurt and the home survived. So this is not to be taken lightly. Here is a dirt cheap, safe way for charging and storage. These are little bags or little packs that you can buy at hobby stores, Amazon, all over these things are widely available. They're very cheap. They're little Kevlar bags with fireproof materials. Excellent choice. Put your battery in this when you're charging it, storing it, or discharging it. Anytime it's not in use, and you can be pretty sure that if they were to go thermal and melt down, that bag's going to get pretty warm, but it's not going to take your house with it. You will find devices like this because especially if you use a bunch of packs, it's a pain and it's time consuming to do all the charging and discharging and all this stuff. These are a bad idea. For the same reason that we want to balance cells in a pack, if we parallel a bunch of packs together that are not dead nuts on the exact same cell voltage, we can cause that heavy discharge between the packs and cause chance for fire or explosion. So these things are a good thing to avoid. Spend a little more money and get a charger that does multiple packs, or just be patient and do one pack at a time. Now I use a lot of lithium batteries, and this is my chosen method for storage. I use Army surplus ammo cans. And what I do is you see them sitting there. This is a wire shelf in my basement, and you'll see that the first shelf is raised up off the floor. If one of those things melts down and goes thermal, that can's going to get hot, so I don't leave it on the carpet. It keeps it safe. I leave the lid cracked a little bit, right, and nothing above it. If that thing goes and catches on fire, it'll probably shoot flames out of that little opening, but it'll do so in a safe way, right, where there's not going to burn walls or anything above it. And then, the one thing to be careful of here is don't pinch the wires in the lid when you close it, because you can start your own meltdown. This is there are many ways to store the batteries safely. This is the way I choose to do it because I've got several dozen packs that I store, and I don't keep too many of them in each can, because if one goes, they're probably all going to go. Storage. There used to be a lot of conflicting data on what the best storage rate for the cells are. There's some generally accepted standards. Battery manufacturers are getting much better at printing the recommended storage level or voltage for a cell. But roughly, you're going to find that Lipo's 3.8 volts, LiFePO 3.3 volts. If you aim for somewhere between 40 to 60% of full charge for your pack, you're going to extend the life of your pack significantly. Don't store them full, don't store them empty. Storing them at room temperature is a really good idea. Too hot is very bad for the cells. Cold does not actually reduce the life of it says depletes life. Cold is not really actually a problem for batteries, but it is very dangerous to charge a cold lithium battery. So if you do have your batteries somewhere cold, please let them warm up, bring them up to as close to room temperature as possible before you charge them. Now, remember I said most of the lithium batteries are not in hard cases, though. This is a very typical radio control battery where it's just shrink wrapped. Everything is soft. If your battery is swelling in any way, shape, or form, please transport it and recycle it safely. Don't use it. That battery is going to fail. That battery, you are asking for trouble. If that battery shows any swelling like that, it is going to fail, and it could very well fail catastrophically with fire or explosion. Puncture is another one. Puncture hazards and shorting hazards are very, very dangerous. So take extra precaution that you're not going to pinch a wire and short it or drop something sharp. And, you know, like a kitchen knife, apparently. So I chose that picture. All right, we're about to wrap up here. We're going to talk about discharge and then let everybody go get another cup of coffee and wake back up. We said that we don't want to store our batteries charged. So that means that we'll have to, at an occasion, discharge a battery so that it can go into storage. Reasonable estimation of degradation for a fully charged LiPo, 20% of its capacity in a year if it's fully charged and kept at room temperature. That's not bad, but you know, if you discharge it, you're not going to lose 20% of its life. You'll lose 40% of its capacity in 3 months if it's fully charged and kept at 140 degrees. Storing this thing up on the top shelf of your garage in the summer, you're going to kill it much, much faster. And here's the warning about cold. It's not really going to damage the battery, but it's very unsafe to charge. The rule of thumb I use, if it's going to sit idle for 2 weeks, I discharge it to the storage voltage. Now, one piece of advice on dischargers. Many good quality lithium charging stations advertise that they do discharge. Don't use them for discharge. They often use the same transistors in there to switch charge current, and they use those for discharge as well. However, they're typically undersized for the discharge current. And instead of using something like a wire wound resistor or some type of good load, they use a pulse width modulation on that transistor to switch the battery directly to ground, which generates a tremendous amount of heat on the transistor, and they fail. I can't tell you how many good quality chargers I've had completely fail when I use them for discharge over and over again. So instead, use something designed for this. The one on the left is something I use often. It is dirt cheap. It's a little Chinese thing. I think I got it on Amazon for 20 or 30 bucks. It uses 350 watt halogen light bulbs, which I just keep in a mason jar for because they get very hot. This charger is completely programmable. Discharger, excuse me. You can discharge lithium, lead acid, anything you want. It's powered by the pack itself. It will balance discharge as well so that your batteries end up at exactly where you want, including a balanced discharge for the cells to end up level. That is a really easy, simple way to do it. The CBA will do it. Or the one on the right is a Sky RC. That's a heavy discharger that will allow you to discharge at very high, I think 35 or 40 amps if you want. It's best to use it with that little Lipo pal that can watch. That'll balance the discharger on the bottom will do the heavy discharge. And then as it narrows in on the target, the Lipo pal up top will balance discharge the last couple tens of milliamp hours on the cells. And those are not terribly, none of these solutions are terribly expensive. Certainly the one on the left is the cheapest. Again, it's best to use a discharger that can balance the cell voltage. It's okay to mass discharge to get kind of close to, but balance discharge to the final level if you can. Careful not to over discharge. If you run a lithium pack to dead zero, one time, a brand new pack, you can destroy it forever. So be very careful about trying to keep it in its usable range. Just like charging, don't leave it unattended and make sure it's discharging in a fire and explosion proof container. And then use a reasonable discharge rate. If the battery is rated for 35C, that doesn't mean you should discharge it for storage at 35C. And often what you'll find is that you'll discharge it at 35C and you'll hit that voltage where it cuts off and the battery will rebound, and it's not truly discharged to the level you think it is. If you creep up on it a little slower, it's a much safer and much more accurate process. And that wraps up lithium batteries. So I appreciate everybody's time listening to that. It's a lot of information and some a little bit dry. And I guess at this point, I'd take some questions if there's any.
James, I guess I had a question which goes back many years when I was told this, and I just looked this up and it's not necessary. They said that you need a Class D fire extinguisher to put out lithium fires, but apparently not. From what I read, you can use any ABC extinguisher to put that out.
My understanding is that ABC is adequate.
Yeah, and they said don't use a Class D, which surprises me because it's metal. It's a metal fire extinguisher, but I was surprised to see that.
Yeah, everything I've ever read about them says ABC is appropriate and adequate. So I hope I never have one of those fires to put out, but if I do, I hope it's in my little bag or box and I don't have to worry about it too much. You know, I was just talking, I can't remember who it was. When I gave this presentation, I think it was at Birmingham University, I was talking to someone that said they had a pack go up on them. I think it was a laptop battery that exploded while it was sitting in the passenger seat of their car while they were driving down the highway. So it's possible at any place and any time.
James, this is Roger.
Hey, Roger.
How does Elon Musk get away in his charging stations with what they call a 25-minute charge, like at a rest stop? That seemed to me to be putting an awful lot of energy into a lithium battery.
Yeah, so lithium is one of those things that's got as many caveats as it does, you know, everything else. And one of the ways to do that safely is by lots and lots and lots and lots of small cells. So you're actually dividing that current up across all those cells, and the current per cell isn't that great. Now there's also some magic in those, of all those lithium chemistries, there's also 24 other chemistries that can take those charges, you know, differently. There's chemicals they can mix in with the electrolyte to accept a faster charge. Science is changing constantly, so you know, that's another one of those, you know, if you have the kind of money to develop and create those kinds of batteries, you can make them capable and safe of doing that, but they're going to be much more expensive than your commodity things that we buy off the shelf.
Also, with the car batteries, I've seen in every case that they don't advertise fully charged. They say it's that 80%. You can't really get around the physics part of that.
Yeah, you're absolutely right about that, Jeremy. And you know, the other thing too is that some of these battery management systems and whatnot, if you just simply current limit the amount in and out and watch the cell terminal voltage, you know, because the batteries don't have memory issues and things like that, it's sometimes cheap. The technology's gotten cheap enough now that you just throw some extra cells in there and you just don't worry about it. You know, you may not be getting 100% of what the cell is actually capable of, but with the protection circuits on there, you just jam as much current in as you want. They take care of each other. They stop at that 80 or so percent level, and you know, they last a long time. There's nothing unlike a lead acid lead acids. If you don't charge them to 100%, if you just take them to 80%, they'll still sulfate a little bit. That problem doesn't exist with lithium. So there's actually really no damaging reason to take a cell from 80. You know, if you only ever use it to 80%, it's fine. It's actually not going to shorten the life of the cell or damage it. You just don't get all the capacity it's capable of delivering. And boy, to talk about what they've done. Here is a Chinese lithium battery that I've picked up. This battery weighs just under 5 pounds. And you can see from the size of my hand, that is a 20 amp hour, 12.8 volt battery. And as you can see from the top, it just has regular terminals. If you read the instructions on this, they tell you to charge it, you just hook it to a 14.6 volt DC source and let it go until it's drawing 0 volts. The battery management system in there takes care of all the balancing and all of the equalization and everything else in the current limiting for the cells. So the technology has gotten much, much better. And let's see, balance issue when using a non-1P pack. I should have mentioned that. I think I do mention that in my longer presentation. So, you know, I talked about how critical it is to keep your cells balanced. But if you look at a 2P or a 3P pack where you've got paralleled things, the critical issue with that is that you use cells that were, you know, cells with fairly good tolerance that were manufactured together. The reason that paralleled cells are fairly safe in those packs is that they are, for the entire life of the cell, they're permanently connected together. So if it doesn't completely eliminate, you know, the fact that one cell could fail instantly and let the other one dump into it, but it's far, far less likely since they've been bonded together and charged and discharged together their whole life. The parallelization inside of the pack is safer than you know, paralleling something that you just do so by connecting. What else did we have here? We've got Jerry asked about Agm Car Battery. You know, so if you're looking for a vendor recommendation here, which I'm not paid by anybody, so I personally really like the latest version of NOCO chargers, the NOCO Geniuses, and I really like Deltran chargers, any kind of the battery tender lines. Those are just great chargers. They take excellent care of batteries. So if anybody else has got great experience with any, please feel free to speak up, but those are my 2 favorite brands. Do you have a question, Dave?
I do.
Or comment?
Thanks, Ed. Dave, WA1JHK. You've talked a lot about the cells and the cell packs and the chargers available for those. What about vendors supplied solutions? So my example is going to be a Motorola handheld, and they have an Impress. They call it Impress as their technology, is their packaged lithium-ion solution. We don't want to scare people off from using lithium-ion in their handhelds if possible. So what do you have to say in that area?
I got one comment to that, Dave. The orange light. Right. So here's the thing about lithium is a fantastic technology and is really well suited for things like HTs and whatnot, because we have a higher power density, and lithiums will deliver their rated voltage. Their discharge rate is fairly flat, and then they drop off very fast at the end of charge, versus a lead acid or alkalines that slowly taper off. Now, if you look, that pack you just held up, there are several things safety built into that for safety. Number one, the cells are very likely in metal cans inside of that, like a double or triple A battery. The cells are probably inside of a metal can. On top of that, the cells are then in that hard impact resistant plastic case. There's a tremendous amount of protection to the cells in that battery. Plus the fact that it's Motorola, so it's got unbreakable anium in all of the parts that make it impossible to destroy. But you know, so the safety factors have been built into this. That also has a battery management system in the pack. That battery will, if you notice when you're using that radio, if you ever been like on a NiCad Pack HT, and as you get closer and closer to the end of the life, when you hit transmit, you'll see the display dim down. That doesn't happen with those packs. Those packs will stop and they will just cut off the power to the HT when the pack is at its safest discharged rate. So you may hit the PTT button, but when you do that, it's going to shut the radio off and not come back on, and it's going to be just sit in that state until you recharge it. Further, that battery and the Impress chip in there, there's a little microprocessor in that battery that communicates with the charger, that talks to the charger about how many times it's been charged, when it was first used. You know, there's all kinds of safety built in there so that the charger can safely bring the battery back up to where it belongs. And the charger is, the neat thing about Impress, the charger will tell you when it's time to replace that battery. When you're not going to get the expected life out of the HT for the day, the charger will say it's time to replace it. So that was so you touched on Motorola, which happens to be one of my favorite brands of things. However, the concept applies generally across the board. If you encase the cells in a metal case and then you put them in a plastic case, you know, if you protect the battery, the scariness of lithium becomes far, far less. Battery management systems, also a good battery management system, and that battery in your hand, this battery right here has one. If you short this dead across the terminals, nothing will happen. It'll make a big spark at first, but the battery, it will sense that. That battery management system will sense that, and it will disconnect the battery. That little Motorola will do the same thing. If you short those terminals, it will disconnect the battery so that the batteries can't go thermal. So, you know, I guess the moral of the story is lithium is something that you should be excited about, not scared about, but make sure all the protection systems that are in place, you know, are in place when you go to use it.
Any experience with ICOM, Kenwood, Yaesu? Are those guys delivering lithium now?
I can't imagine they're not, but I don't know, to be honest with you. It's been a while since I've bought one of the Japanese branded radios. I think all of the batteries I have are still NIMs, nickel metal hydrides. I just can't imagine that they're not lithiums by now. But I honestly don't know the answer to that.
My Kenwood D74 uses lithium ion.
Yeah, there you go. No, Roger's holding.
Roger's got one.
Yeah.
Yeah, I had a comment about AGM car batteries as well, if you're interested. Back at the beginning of the pandemic, they sent me home to work from home. So there was no requirement to go out in the garage and start up the Jeep and drive it down the street. So I didn't start it for 5 weeks. And when I went out, the Agm battery was dead. And the learning is that the newfangled cars all have a small trickle discharge at some rate. And I'm an Interstate battery fan, so I went up to Interstate and picked up a new battery and said, how often should you start one of these newer cars? And the answer was about every 10 days. So the learning is, rather than spend money on a brand new Agm battery just because you didn't start your car, you should drive a little bit, or if you got a couple of cars, rotate them so that you don't ruin a battery just from leaving it sit idle.
And I'm partway through I tried to find them commercially and found that only high-end sports car manufacturers make them. So I'm building them myself. I actually am building magnetic charger ports for all of our vehicles because we have the same problem. We don't drive enough now that we've been sent home. Is such that there's a little stainless magnetic, rare earth magnet charger port on the front. I'm putting them in the grills so that I can just attach a battery tender port to each. That way, if I forget when I back away from the garage, it'll just disconnect and fall to the floor, but it keeps the batteries charged all the time.
I like it.
Great transition to a question from Chad. What are your thoughts on the Deltran battery tender solar charger to keep the batteries maintained?
They're great. You got enough sun to do it. They are absolutely great. Deltran's been in this business a really, really long time, and they have it figured out. I believe a lot of their designs do still use the Unitrode 3906 chip in their designs, and it's just a rock solid 3-state charger. Yeah, the Deltran solar ones, I know several people using those, and they work wonderful. Just looking back, I think I caught everybody's. Any other questions? Oh, Roger, I think you're mute if you're talking to us.
Yes. This Agm battery just is a lithium-ion battery pack, 7.4, 1880 milliamp hours, 14 watt. But it is lithium, fairly small.
I would be highly surprised if almost all of the new Agm battery, HT batteries weren't lithium. I think that lithium has just become the de facto standard for everything.
Yeah, I noticed they built this into the 705 as kind of the maintaining battery, and also on the 51, and I expect the 52 when it's available.
Yeah, and that's no surprise. Well, if there's no other questions, thanks everybody for attending today and listening and participating here at the end.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. For more information, visit our website, ncarc.net. Thanks for watching, and don't forget to like and subscribe.